welcome. How you doing? You bet. You bet. So today we're going to be talking about image quality and how we can evaluate it using a phantom. And it's near and dear to my heart. And I'll start it off by telling you a little story. I was a training director for Conquest Imaging before we became part of MXR. And I had all my engineers in for a weekend to kind of get us all on the same page and talk about the same things. And one of the concerns was how we use a phantom. And I had 8 engineers in the room, and I asked my senior engineer to go ahead and do some phantom tests as he would during a preventative maintenance. Then I had the junior engineer leave the room before he did it. When he was finished, we had all the results that he collected. And then I had the junior engineer come in from the group and perform his PM testing. And now we're an ultrasound company, and we supposedly train all of our engineers the exact same way. And we got 2 completely different results. And why, you might ask? Well, they didn't use the phantom the way it was intended. So our senior engineer actually did a really good job, not, coincidentally, he'd been in the ultrasound industry for 25 years. Our junior engineer, on the other hand, had made some assumptions on how to use a phantom that were completely inaccurate. So part of this is an effort to try to build some consistency throughout the imaging community on how to use a phantom to evaluate image quality. So that's kind of where we're going today. Please, if you have any questions, speak up. It's a very informal lecture. The more questions, the more we all learn. So now we're not working. I checked this before I started here, and it was working. So now it's not. Great. I even checked it. I don't know what happened. I can do it manually, but I was hoping not to have to hit buttons. Yeah, I know that. I don't know why I would go to sleep, but that's what I'm trying to do. There we go. And now I can't even see the mouse. There we go. Try it again. And I wonder if the battery's dead. I don't know. It might be their battery because I'm not getting the laser pointer either, which I don't care about. But I'll do it manually in the meantime. So we talked a little bit about what we're doing. It's understand the image principles of image quality, frequency and resolution, how they work together, different types of resolution. We're going to talk about all this today. I only have one phantom. I'll please pass it around as we're talking, or come up afterwards and we can see it in hand. It's hard to see from way back there, I know. But we'll talk about it and how to use it. The different tests. There's going to be 2 presentations basically today. The other one I'll open up at the end. And it's a document that I did not create. I found it online just like everybody else did. I found it online several years ago, many years ago. And it's just 8 pages, and it very specifically shows you how to do testing, but it's in really nice, simple English. So we know when we get into some of this ultrasound physics, it doesn't look like battery's working, but I don't know that to be true. The laser pointer is not working. So thank you, appreciate it. I have another one if you want to use mine.
Oh, if you got one, I'll swap that.
I don't know if its battery's working, but I have it, yes.
Sorry about that.
Oh, you're fine. I carry one because a lot of times they don't have them, but probably want to get yours out and see if mine works. There we go. Thank you so much. All right. So now we'll get started. So what is image quality? Why is it important? Image quality, it's really funny in ultrasound. How many here work directly with ultrasound? Anybody? When you encounter a problem and they're trying to describe a problem, they use really very definitive words like mushy. Well, what's mushy mean, right? I mean, you're trying to put a word to something and, well, it's broke. Well, thanks, it's broke. But what do you mean by broke? Well, the image is mushy. That doesn't help us very much. How about grainy? How about washed out? So we have a lot of terminology that the technologists will use, but it's really hard to say, okay, I know what you're meaning to tell me. I understand it completely. So one of the things that we have a great deal of difficulty doing is getting a clear picture of what the technology is trying to say. So makes it kind of hard to solve the problem if you don't understand what the issue is. So one of the things we can do is check to see, has this image quality changed over time? And the way we can do that is when you bring a new ultrasound system into your hospital, the very first day it comes in to be examined and checked and electrically safetied, all the things that we need to do to put a piece of equipment into service, you should do an image quality check with it and capture photos, capture printouts. Whether you send them to PACS as a point of reference or you have a physical printout of them, you should capture these images, because 3 months later, maybe the technologist is trying to describe a problem to you, and it's not a tangible artifact. A tangible artifact's easy. It's a big line going through your image. Well, it's missing data. It's not there. That's easy to see. But when they start talking about mushy, washed out, grainy, all the other subtle things that they're talking about, you can simply bring your Phantom back out, do another set of images and compare them to the last set and see if you've seen a degradation over time. And, if you're talking about a lot of your accreditations, American College of Radiology, there's some cardiac accreditations. One of the primary things that they have you do is do the exact same test every 6 months, every year, so you can then go back and look at your the previous year and say, is there degradation over time? So it's really important that you evaluate that and have a tool to evaluate it. And one of the ways you can do that is by having these captured images, and you keep them with the machine if you can. There's no sense in taking pictures on your phone unless you're the only one that's going to work on the system, right? So you take pictures and leave. 3 months later, somebody else goes in to evaluate the problem. They have nothing. So it's really best if you can send them to PACS if you have to, print them out from a reading station by PACS, and then leave them with a system. So there are tools out there that we can use. In the customer interview, I actually changed this little bullet. I no longer do customer interviews. I do customer interrogations because for whatever reason, they don't want to tell you what the problem is. And you say, well, that's not true. But in reality, it is. They'll tell you what's mushy or it's broke or it's not working right, but they won't tell you what information they may have. And I'll give a short story on that too. I went in to work on an old Logic 9. And the old Logic 9s had a recurring problem. It's known. They get a color artifact on them. And the way you fix a color artifact is really simple. You go in, you kick the right-hand side of the machine. And you don't kick it really hard, but you kick it and the artifact goes away. So I get a call one day from one of my sonographers. His name happened to be Eli. And he says, dude, I got a color artifact on my Logic 9. I said, well, did you kick the side of it? He goes, I know, you've told me that one. It's still there. He goes, it's much worse than that artifact. I said, okay, I'll come out and I'll look at it. I went out and looked at it, and sure enough, it was color everywhere in the screen, in the color box inside of it. And the very first thing I say, well, multiple probes and multiple ports. So I try a different probe. Now the first one was linear, the second one's curved. Both have color artifacts in them that made it unusable. Okay, so it's not a probe related problem. So what do I go in and do? I start troubleshooting. I don't have any parts. I got there the same day. So one of the things we can do is reload software. So I reloaded software. Didn't fix the problem. I didn't think it would, but at least I could try to do something that day. When I'm back on day 2 after ordering parts, I ordered a power supply, specifically a front end power supply. That didn't fix it. Day 3, I went in with a new computer system, which also involved a software reload. That didn't fix it. Day 4, I ordered 2 more parts that are called time delay boards. Put those in, that didn't fix it. I'm running out of electronics to replace now. There are 3 boards left. The probe interface, where you plug the probe in, a control board, scan control board, and a B&M mode processing board. So I ordered all 3 of them. Day 5, I came back, I put all 3 of them in. It didn't fix the problem. There were no electronics left. I still have not fixed the problem. And I'm kind of angry, right? I'm like, wow, here I am on day 5, put a lot of effort, put a lot of resources into this, and I still haven't fixed the problem. So I go back and I get Eli and I said, hey, I need to talk to you for a minute. You got a minute? He goes, oh yeah. He comes in there and there's boxes everywhere, parts everywhere, computer everywhere. It's just torn up and put back together the best I could. And I said, I have replaced every electronic piece in this system and I still have the artifact. I said, so I have to start over. I'm not sure what I'm missing. I said, I've checked multiple probes and multiple ports. He goes, well, I have another one in a drawer over here. I said, okay. So he goes and he gets it, he hands it to me. I plug it in, there's no artifact. Well, wouldn't that have been nice of him to tell me on day 1, right? Because then I would have known it was probably a probe problem. But he didn't, but he knew about it. And that's what I mean. Trying sometimes to get the information that he had on day 1, to get him to say it out loud is kind of tough. So I change it to an interrogation. Yes.
So I'm going to fix a piece of equipment. It says it's not working. I said, nothing's working around here. And they look at me like I'm crazy. And I said, don't tell me it's not working. Tell me what it didn't do yesterday it's doing today. And that's how I usually get them.
Right.
Because a lot of times they'll say, oh, it's not working.
Yeah, it's broke. Well, what's that mean?
No, they'll just write it broke. I'm like, so what's new? So usually I just find the text and I said, tell me what it's not doing. It did yesterday and it's not doing today. You know, a lot of times you'd be surprised, you know.
Yeah. They know. I mean, they wouldn't be complaining about nothing, or generally they're not, right? But trying to get that information from them sometimes is difficult. So, you know, again, that's why I go over my image, you know, my customer interview, because Eli knew the whole time. Whether he wanted to admit that or not, he went to the drawer, pulled it out, plugged it in, and it was fine. And I'm like, okay. So next day I ordered 2 probes, got them there, and everything was back up and running. 6 days into it, right? 6 days. So image quality, it's a big deal. It's hard to troubleshoot. Ultrasound's very subjective. You might say, well, I don't like this image, and somebody else says, well, that's a great image. Very subjective in ultrasound. One of the fundamental principles that we like to talk about in ultrasound has got to do with frequency. Frequency is a funny thing, okay? The higher the frequency, the less it penetrates, but the better the resolution. Okay, so you get this high frequency probe and you can see really good images, but you have probes that will only go this far into your phantom. Now, they have 33 megahertz probes out there now, which is unheard of. And they only go, you know, 1.5 centimeters, 2 centimeters into the human body. They're very surface oriented. The image is amazing, but Canon makes those, just so you know. But it's a principle that we have to be aware of. Then they have the lower frequency probes, which is down in the 1 megahertz range. So traditional ultrasound frequencies run from about 1 megahertz to 20 megahertz. When they get above 20 megahertz, they become very specialized. Okay, so 1 to 20 is a really good kind of characteristic of ultrasound probes. And the lower the frequency, the more they can penetrate, but the poorer resolution they have. It says up here axial resolution. We don't need to worry about that yet. I'll define axial in just a little bit. But it's resolution, better picture, worse picture, right? That's what we're really looking at. See? And here's your axial and lateral, just a demonstration of what they are. Axials top to bottom, laterals left to right. We'll talk more about the definitions of those in just a minute. So here's some things that when we talk about image quality that we need to be able to understand and use our Phantom to help us evaluate. Detail and spatial resolution is the ability to distinguish small structures, and it goes on both axially and laterally. Again, on the next slide, we'll start defining axial and lateral, so we're getting there. But they're very small objects that are close together, and it's whether we have the ability to determine that they're two objects or if they blur together into one. So that's really what we're talking about. Okay. Image uniformity, comparable detail and contrast throughout the image. ACR, as an example, American College of Radiology, asks if the sides of the image, the edges of the image are the same as the center of the image. They want to make sure that what we're looking at is uniform, both left, right, and top to bottom. Okay. Contrast resolution, the ability to differentiate different tissue types without introducing noise. These are different tissue types. Again, if you want to come up here later on, or I'll pass this around. These are the different tissue types. Very, very dense is the white, and the least dense is the very dark. Okay, so these just represent different density materials. As the Phantom is talking about, that's the different contrast that you're going to see. Okay, temporal resolution or frame rate is the system's ability to refresh the screen. Okay, refresh it normally is around 30 times a second, 30 hertz. It varies based on the frequency of the probe and whether you have transmit zones, multiple transmits and zones. But in reality, it's just how fast the screen is being refreshed, the image area, not the whole monitor, right? Just the image area. Dynamic range, largest and smallest signals. What's the least dense versus the most dense? You want to make sure that you can limit artifacts or reflections from other locations. We're targeting a single point in space when we fire an ultrasound. We call it a transmit because what we're doing is we excite the crystals in the probe, they vibrate, and it sends a sound wave into the human body. Well, that sound wave expands like a wave, like you drop a pebble in a pond, so it's going to strike everything in the human body. But we specifically target one point. And how do we do that? Because we're looking for what we call a time delay. So we transmit with a known time associated with it. So we're targeting a specific depth. And then we wait for an echo to come back at the exact same time, right? So we're targeting a point in space, and we know when the echo is going to come back from that point in space. And based on the amplitude of the echo, we know the density of the object. The more dense, the larger the echo. Does that make sense to everyone? Kind of how that works? So we're doing that, and we're able to determine different densities in that manner. As I said, we're going to talk about axial resolution. Axial is two objects that are very close together. So the two blue objects represent those objects that are close together, one on top of the other, or as they like to say, parallel to the beam path. That's the ultrasound beam path coming from top going down. Okay. And what we're trying to represent here is if we move these two objects down here into this, what we call the far field, the depth deeper, would we be able to see those two dots? Does anybody have any idea on how that would work? What would they look like? Anyone? I know some of you worked on ultrasound.
Look a little bit more, not as crisp, because the further you out, depending on the frequency of the probe, you know, the high frequencies is going to not look so great. You're going to need to switch over to a lower frequency.
Well, lower if you need to go deeper to get to them, right? Higher if you want better resolution. So it's kind of a trade-off. But if we moved them, he's right, they become less clear. And what less clear means doesn't mean you can't see them. It means that they're gonna become fuzzier. They're gonna become bigger than they really are. They're not as defined. And when that happens, they'll blur together and look like one larger dot. Okay, so these two will no longer be able to see. Well, the same thing happens if you put them up here. Because we're not focused right there, they're too close to the near field, they will blur together as one larger object. So we're always looking for that in phantom testing. The specific definition says parallel to the beam path. I prefer to say axials top to bottom, meaning they're two objects, one on top of the other. Then we have lateral resolution, left to right, means side by side. Shows two objects again, right in the middle where we're focused. And these curved black lines represent where we are focused. They're not real, they're just telling us in this representation that we're focused right here. So when we focus in that area, we're going to be able to see the two dots independently. But when we move into the far field or too close in the near field, they're blurred together as one object. Okay. And the Phantom gives us a tool. This is a picture basically of the 539 Phantom that I have up here. Okay, and on the Phantom, you have this array over here called the resolution array. They have objects that are very close together, both laterally and axially, and it transitions as it curves. So you can take an image of that, and you should take an image of that. There's no accreditation out there that requires this. In other words, they don't tell you, well, take a picture of the resolution array. But if you have that, and 3 months later, they're complaining about image quality and how it's suffered, where you can use a resolution array and several images from your different probes to say, well, yeah, it does look different, or no, it doesn't. So it gives you some place to start for sure. All right, any questions on axial and lateral? Top to bottom, left to right. Okay, so if, I know it's hard to see, but on these objects here, can you tell me whether that is poor axial or poor lateral resolution? Anybody?
Poor lateral, because the dots on the left kind of are the 2 or 3 dots or whatever, they're kind of one.
Yeah, you can't even really tell how many there are there? So yeah, it's poor lateral resolution. Okay, so you've said it's poor lateral. Now, can you tell me if that's a probe related or system related? And that's a trick question in of itself. And why is it a trick question? Well, because there's no information up there. It doesn't tell you if it's a 1 megahertz probe or a 15 megahertz probe, right? So you really don't know. If it's a 1 megahertz probe, do you expect good resolution? No. So this may be normal. But that's the point. If you had a picture from 3 months ago and you could see all the dots, and now you're taking the picture, same probe, same settings, and it looks like this, you know there's a problem. There's been degradation over time. So this is a good way to try to get it into your mind what we're looking for when we talk about axial and lateral resolution. And then transverse resolution goes one step further. If you were to pass this around, and I highly recommend you do it, but it's hard to see through the top of this one. This is kind of old, but I use it to travel with. There's this object right here. The top one is very dense, but it's a cylinder, goes all the way through the Phantom. So it's one object that goes from front to back, right? And so when we scan with our probe, say it's a linear probe, we scan it, and what we'll see on our monitor is a cross section or the circle, like it's displayed on the Phantom, correct? So what if that, instead of having a solid bar, if you will, a solid object going from front to back through the Phantom, what if it was two marbles, one in the front, one in the back, and I was to put my probe right in the middle? What would I see? Nothing, because I'm not taking a cross section of either one of the marbles, right? In order to see the marbles, then I'd have to change the position of my probe, right? Then I would be taking a cross section of both marbles, and I would see two circles side by side. Well, in this case, what it's asking me to do, though, is look at the two objects front to back. And can I do that? We just said that, you know, if I'm right in between them, I can't see two objects that are one in front of the other. So when would I be able to do that? That's when we have a 3D probe. Okay, so transverse resolution only applies to a 3D probe. And that's the whole point I'm trying to make when we're talking about it, because in standard, ultrasound, we're doing 2D imaging traditionally, right? Two-dimensional basic imaging mode, whatever you want to call it. It's two-dimensional. When we get to 3D, then we can see objects front to back. But at that point, we'll be talking about transverse resolution. Now, there's no requirement by any accreditation agency to measure transverse resolution. And can you do it on this Phantom? It's not easy because, again, there aren't objects front to back. They're all cylinders. They're all going all the way through the Phantom. But if you were to change it this way, then you could see objects that are going front to back because now their orientation is this way. Does that make sense? So yes, you can kind of use a Phantom, this Phantom, for 3D imaging and do a measurement, but a lot of the probes won't fit in this gap. So it's really how you use it and what you're using it for. Okay. Transverse resolution. So image uniformity, we want to talk about comparable detail and contrast throughout the image. Should not look different from top to bottom, left to right. And again, we're talking about the image area only. Okay, so we wouldn't want it dark on the sides so that we couldn't see the object the same as it was in the middle. So this is a pretty good 2D image, black and white, or B mode. Okay, another name for B mode is grayscale imaging. So don't let them mess with you, because a lot of times the terminology is what catches you, right? They may say, well, I have noise in my grayscale. And you're like, oh my God, what's that? What's just 2D imaging? Okay, that's all they're talking about. 2D, B mode, and grayscale all mean the same thing. Okay, so in this case, we have a pretty good image, but I have a question for us. What about these dark spots, like right here, this shadow, this dark spot? And there's one here too, where it just kind of, you lose image. Is that a problem with the system? Is that a dropout? I'm sorry?
Oh, because if you see on top of that, it looks pretty clear.
Right.
It's getting further down into the tissue, it's not getting that type of resolution.
Right. So in reality, would you think to associate that with the probe? And the answer is no. There's a reason for that. If it was originating from the top, absolutely. Then you could say we probably have weak crystals or dead crystals, right? It's been dropped. In all likelihood, the cable's been ran over. Something happened. But in reality here, what we have is we have the hand, a baby's hand, and another hand. So it's going through a lot of bone, and it gives up acoustic energy. So what you get underneath that is a shadow. And the same thing is going to happen on your Phantom when you're imaging from the top going down. This is going to take up a lot of the acoustic energy. It's very dense like bone. So you'll get a shadow underneath of it. So in order to do a test to see if you can see all these objects, turn it sideways. It's one of the reasons I love this Phantom is now they're very close to the top, so I can use low or high frequency probe. And I just move across and see if I can see all 6 objects. Okay, so contrast resolution, you want to be able to see all 6 objects, and you want to see that they're different. Does that make sense? Because they're different densities, right? So when we look at these 6 objects that we have, we want to not only see the objects, yes, I can see them, but we want to see that this is different than that. And they're very close. And it says in the definition of contrast down to 3 decibels. And you can see it starts at the top 15, and then 6, then 3, then -3, 6, and 15. What does a positive and negative indicate? Did anybody have any ideas on that? Why positive and negative? Yeah, absolutely. And what do we base 0 on? Well, 0 is the average density of human tissue. So in ultrasound, we had to come up with what is the average density of human tissue, and that's 1,540 meters per second as far as how fast sound travels. As density changes, the speed of sound changes. The more dense the object, the faster it travels. The less dense, the slower it travels. So we know that we have different density objects here. 0 decibels represents the average. It means it's exactly the average. If it's more dense than average, then it gives a positive. If it's less dense, it's a negative. So up here would represent bone, and down here is approximating air. Basically, we don't get a good reflection from air, right? Or fluid for that matter. So any questions on contrast? Now, the funny thing is, for example, American College of Radiology does not require you to capture information on contrast resolution, which I find amazing. But you should do it. Clearly, if they come back later on and say, you know, what's the contrast? My contrast resolution's messed up, and you go and check it, then you won't know what it looked like 3 months ago, so you won't know if it's gotten better or worse or changed, right? Another question I have about axial and lateral resolution versus contrast resolution. What probes do you need to use to check axial and lateral resolution? What's the requirement? All probes. And why? Because different frequencies have different resolutions, right? So you need to evaluate that probe for its set of frequencies. And then you put a different probe on or select a different probe with different frequencies, and you also want to evaluate that one. But what about contrast resolution? Do you check all the probes with contrast resolution? And the answer to that is there's no requirement to check it in the first place. But secondly, you should check it, but you only need to check one probe, because it's really not the probe that establishes the contrast resolution, it's the system, right? So if the system can resolve down to a specific frequency, then you're good to go. The probe, the fact that you use different frequencies, they should all be able to see different densities. Does that make sense to everybody? The different density isn't based on the frequency. The actual accuracy of the picture is, but for determining the density of the material it's viewing, frequency isn't a factor. So you only need to check it on one for contrast resolution. So does that make sense to everybody? Temporal resolution, I talk about the frame. It's basically how fast the image area itself, only the image area, gets refreshed. It's normally in these set of numbers, which I know you can't read, but they're up there. Keep in mind, people tell me all the time, I teach class throughout the entire year. Last year was a slow year, but the year before I taught 400 and something people. And people always say it to me. You'll see it in the description, either here or over here, it'll say FR, okay, which stands for frame rate. But a lot of people, because it says hertz after it, say it's frequency, because FR sets you up for frequency, right? And it kind of is. It's the frequency at which the screen is, or the image area is refreshed, but it's not the frequency of the probe. And that's the caveat I want to make sure everybody understands. The frequency of the probe will be in megahertz. And on, for example, a Philips system, it doesn't tell you what the frequency of the probe is. It tells you whether you're in G, P, or R. And you go, well, how's that help me, right? And it's not very intuitive. G is general, P is penetration, and R is resolution. So your penetration would be the lowest frequency for that probe. Your G would be middle, and your R would be the highest frequency for that probe. But it doesn't tell you what those frequencies are. And that's, for example, on a Philips. Other systems do it, but Philips is, yeah.
Did they set an industry standard for those three rates? Is there an industry standard that would set those?
Nope. I wish there were, but technology is becoming wonderful, right? In the old days, a probe may only go from 2 to 5 megahertz, and now they're going from 1 to 9 megahertz. So there really isn't a standard that would say exactly what they are. I would say most of the probes, and this is again general, I wish there were a naming convention that made sense, but a 2 to 9 megahertz probe, I would say that the base frequency for penetration would be 2 megahertz, and the resolution would be 9, and somewhere in the middle, 4.5 would be your general resolution rates. But it doesn't, there's nowhere for me to know that.
I was just wondering, I know Chris has a question on there about that.
I wish there were, and it seems like there should be some way of knowing that, but I can only tell you the range of the probe, and I assume they're using its lowest and highest range, and in the very middle frequency. But it doesn't. There's nowhere you can find that on the system itself. Clearly, frequency affects it. The higher the frequency, the more times the faster it can refresh the screen. Number of focal zones, and it's hard to see on this, but right here or over here on the edge, one of the edges will have an arrow or a bar, and you can change the length of the bar, or you can move the arrow. But you can also add arrows, which are called focal zones. As you add focal zones, your frame rate will decrease. So keep that in mind. If you increase the length of the bar, your frame rate's going to go down, because you're telling the system, you have to take this whole image, but I really want to focus here instead of just here. So as you change the length of the bar, you increase the length, you decrease the frame rate. Yes? Well, it's really more of a function of frequency, because we have to be able to if you have just 10 megahertz probe, you fire it 10 million times a second. So you can't fire it any faster or slower. You can't process it any faster or slower. We certainly have the ability to process more information, because we use it for like Sono CT, where we do 9 times the amount of information in a single scan. So it's not processing power, it's a physical limitation, because we only can fire it at the frequency the probe is designed for. Dynamic range, largest and smallest signals acquired. I've already kind of described that. We have the least dense versus the most dense. So right here, you have your amniotic fluid, which is going to give you very, very little reflection, very little echo. And clearly we have bone, jaws, which is why you get this dark spot underneath because of the density of the jaw. Okay, so not much else we can say about that. We just have very specific limits, and we don't do good with air. There's no echo from air, right? So here's some of the phantom tests that we use. They call it system sensitivity and/or penetration testing. Okay, I'm not sure how they get the term sensitivity. What you're looking for is penetration testing. That's really what you're looking at. Penetration testing is required on every single probe. Okay, I went to Johns Hopkins and taught for a week. And helped them because the engineer there wasn't ultrasound trained. And one of the things they wanted me to do was a PM, demonstrate it for him so that then we could do further PMs and let them do it while he had somebody there watching. And the one they let me do it, had 26 probes on it. It's a personal record. It was ridiculous, but you have to do every single probe. Okay, and it tells you if you're using an ACR accredited form, which all my forms are ACR accredited, it tells you very specifically how to set the system up. Okay, because they want you to be very consistent. If I come in and set it up one way and then another engineer comes in 6 months later and sets it up completely different, we're going to get different results, and that can look like degradation over time. So they don't want that to happen. They tell you very specifically what preset to use, what frequencies to use, what power to use. It's all right in the description of the form. So an engineer comes in that says, well, we want you to be on, we need you to test all the frequencies that probe can do. So that would be your general, your penetration, and your resolution. Okay. We need to set you up with a single focal zone, only one focal point. They don't want to do a range. Okay. They want your gain set to such a level that they can see the max penetration, because that's what we're measuring. That's really the whole point of this test, is to measure the maximum penetration for that probe at its various frequencies. Okay. But when we do that, we also want to make sure that we're using the proper tools. And I told you I had a class and my engineers weren't even using the same measurement technique. If you get close to this, there's a whole bunch of circles going down in rows, 5 different sizes, if you will. And these are the objects you want to use to measure. I have a picture coming up. These are the small objects, and that's the ones we use to measure penetration testing off, is the very smallest objects here. And people often ask, well, why would you use the smallest object? Well, when do you want to recognize a tumor or cyst? When it's small, right? So that's why I measure it, and that's the way they design it to test it, so we can come up with a realistic measurement for how deep the probe will penetrate at its multiple frequencies. Okay, and then you record the maximum penetration capability for that probe. And you might think the maximum penetration capability for that probe would be at its lowest frequency, correct? Does that make sense to everybody? Lowest frequency, max penetration, right? But your resolution may be so bad that you can actually see the small object better using a higher frequency on that probe, which is why they make you test all the frequencies of the probe for the maximum penetration. Does that make sense to everybody? It's kind of subtle, but it is, and you know, we use frequency as a guide, but in reality, when you get to real detailed stuff, the lowest frequency may not give you the best penetration for the small objects. Axial lateral, we already saw pictures on that. Two objects close together. Again, I have another document that I'm going to show here after I'm done with the presentation. 8 pages, we'll go over it. It has just wonderful instructions, how to do the test, what you expect to see out of the test, and it's wrote in very nice, simple English, so we're not trying to be physicists when we're reading it. It's really nice for the common person when we're trying to look at a phantom. Contrast resolution, I spend a lot of time on that. You only need to do contrast resolution with a single probe because frequency doesn't have effect on the system's ability to determine density. Geometric accuracy, we have not talked about vertical and lateral, but again, if you guys take the time to come up here, I'd be happy to show you, but there's arrows on the phantom or measurements top to bottom that define these objects, how far they are apart. So you can measure them using a caliper measurement on your ultrasound and make sure your calipers are measuring accurately, because all your calculations are based on the caliper measurements. So if your calipers are off, your measurements, your calculations will all be off. So they have them both horizontally and vertically throughout the phantom. So you have the ability to check vertical and horizontal accuracy of your calipers. Now, do they vary very much? In other words, do the calipers change? And the answer to that is no. It used to be in the old days, you get a little tweaker and adjust the potentiometer to make them read what you wanted to read. They got rid of all that. It's all software generated now. So in 15 years, I have never had the calipers not meet the specs of an accrediting organization. However, I got a call from a fellow engineer who did. I want to point it out because this has been happening more and more regularly, and I don't know the engineering behind it. I wish I did. Somebody would like to explain it to me someday. On pediatric measurements, they changed the average speed of sound in human tissue. But because the software for the calipers is developed on normal studies, it throws the caliper measurements off when using a pediatric study. So if you're testing your system, your caliper accuracy while using a pediatric study, you might find that they're way out of calibration. A 2 centimeter caliper measurement will end up being like 2.4. It's not anywhere close. Okay, so keep that in mind. If that's the case, change to an adult preset, if you will, and check your calipers again. I bet they come into spec. Okay, so I just like to point that one out because it took me 2 weeks to figure it out. Me and another guy, back and forth over the phone. Both of us had lots of experience, and none of us had ever seen it. And it got down to the preset they were using. All right, so system sensitivity, again, we're just now talking about the test, how to set it up, your ability to display weak echoes from the small objects, as I said. You have to do this to correctly interpret and diagnose. I've talked about that. Max depth is affected by output power. They want you to be at maximum output power. Time gain control, those are the sliders on the control panel, TGCs, right? Gain, which is your overall amplification. Frequency, you have to do all the frequencies for the probe and then report the deepest penetration you can for that probe. And your focal point, a single focal point at the maximum depth you can see. Says record findings on hard copy. Well, if you don't do it on a hard copy, then you really don't have them. The alternative is to create a test patient, if you will, and send it to PACS so that you have it on PACS at a later date. But some hospitals, especially if you don't have access to be able to query and retrieve an old patient or an old study, makes it very difficult. So I really do recommend hard copies, printing them out, sending them to PACS, then going to the reading station and printing them. Whatever you got to do to have hard copies, it really benefits you, the engineer, to troubleshoot later on when they're needed. If you're ACR accredited, American College of Radiology, again, you have to have hard copies. They haven't changed that yet. So for those of you who say, well, I have an EMR or I store them in my computer system, as long as your auditor lets you get away with that, great. But there are auditors out there that will go right to the website and say, it tells you have to have hard copies left with the machine. So it's up to you. We do hard copies for all our customers that are ACR accredited because we don't want to be called out on it. But hard copy is best. Consistent over time, again, ACR, any accrediting organization is looking for degradation over time. Axial, lateral, we already talked about axial and lateral. I just like to bang it out because we just don't do this in ultrasound enough. I've never walked in and said, damn, I have too many pictures of past studies. But I have walked in and said, I wish I had some. So, it's in your best interest to print these out, make hard copy printouts, leave them with the machine. That way, if you're not the first one there or the last one, you have something to work with, right? Just pull them out and look at them and start. Again, consistent over time. Contrast resolution, again, they call it grayscale. Everybody understand why they call 2D or two-dimensional imaging grayscale? They take the density of the object and map it to the grayscale. This is your grayscale. And one of the things that will affect image quality is, especially hospitals that have different sonographers or technologists on the weekend, you'll get a technologist come in on the weekend and they'll like a different scale, so they'll change it. And then on Monday, the normal technologists will come in and they're used to one grayscale, and somebody changed it to a completely different one, and they start complaining about image quality. So be careful of that if you have different sonographers coming in and out of the department. It's very subjective. Some like it more grainy, some like it less grainy. It's funny, but it should stay somewhat consistent over time. Geometric accuracy. I know the measurements aren't on here, but these set of objects going all the way from the top to the bottom, they're indicated on the Phantom. They're 1 centimeter. They're defined on the Phantom. They're 1 centimeter apart. So you take two of them, you have a 2 centimeter measurement, right? So you can use these objects for your vertical measurements. And on the Phantom, specifically these two right here and these two right here are defined as 2 centimeters. Now, the one thing I find funny, they've corrected it supposedly, but these two objects also look like they're 2 centimeters. And it kind of makes sense that it would go 2, 2, 2, and 2, but it doesn't. It doesn't work like that. Okay, if you measure from this one to that one, you might get like 2.25, 2.21. It's much higher than you'll get between these two. Okay, so keep it in mind. It's defined as only these two. When I talked to one of the people who developed this, Linda used to be the owner of the company, made ATS. She sold it. She didn't know that the measurements were wrong there. supposedly it got corrected. This one it's still wrong because it's an old Phantom. But I had to show it to her to prove that it was not accurate in that location. So keep that in mind. All right, so that's the first one. Like I said, I have another short presentation to give you special instructions, but if you guys want to pass this around, just go around in the circle. Do you have any questions for me on this first portion of the presentation? Anything at all? As far as Phantoms?
I've got Phantom, but I don't have this.
Oh, yeah. If you use there's some liquid-based Phantoms. That's a good question. Thank you.
Well, it's still a gel Phantom. It's just.
Really? I haven't seen that one. It's funny.
Got a top that you spot off, but
Interesting.
I thought it was made by the same people.
ATS? Or now it's what CRIS, whatever they've sold out to, because ATS doesn't exist anymore. You can still get these Phantoms. You have to work harder at it. Have they gone up that much? Because it used to be they were around.
We just ordered 4.
Yeah, they were about 2,500.
You might get lucky if you go on eBay and find one that's never been used, it's about 1,500.
Yeah, we actually, and I shouldn't say this, about 2 years ago, found 14 of them that we bought all 14 for $700 each. And it's like, we didn't have a need for 14, but at $700 each, it was like, well, I'm gonna buy them. So, but one caution, I like this style, which is the gel based, as you said, because it never requires calibration again. It's got a 10-year warranty out of the factory, so it never evaporates, it never changes. If you get one that is fluid based, like the Gamex, okay, they have to be weighed annually and recharged if they drop below a certain weight because of evaporation. Okay, so now you have the cost of the Phantom is no less expensive, but you now add to the cost of the Phantom a recalibration annually, and then a recharge fee if required. So I highly recommend the gel-based Phantoms. I don't get any commission. I don't work for anybody. They're easy. I throw them in my trunk. I drive to Flagstaff when I lived in Arizona, and it'd be freezing. I'd drive down to Phoenix. I'd have it in my trunk. It would be 120 degrees. And you just take it in, let it get to room temperature, and it's ready to go. So
I guess mine is the Gamex.
all right.
So I guess it is fluid based, but
Yeah, I've seen the Gamex that are kind of like they're rounded on the edges, but not a round. Anyway, and they are fluid based, and at least the old ones that I'm familiar with are. And you have to have them calibrated annually. So the image quality is great. So I'm not, please don't take anything I'm saying to indicate that the image quality isn't good. Gamex sets it up so their contrast resolution is already going at the same depth. They don't go from top to bottom, they go left to right for the contrast cylinders, but there are only 4 of them instead of 6. So some differences between the different Phantoms again. I prefer the gel-based, but image quality, some people say Gamex has a better image quality. Great, they have better image quality, but I have to have them calibrated all the time. So any other questions on that?
use the ultrasound gel.
No, that's another reason I like the ATS. It's being passed around. Every side has a trough, if you will. You put water in it. And can you use gel? Absolutely. Why don't I use gel? Because especially on like a curved probe, you slide it and then the gel doesn't couple. So you get like what looks like a dropout. It's just because the lens isn't coupled to the Phantom, where water's fluid and it stays coupled as you move it around. I prefer water. The other thing you can do with this Phantom, if you're completing electrical safety during a PM, which we do, you can use the water in the Phantom and just put your clip from your safety analyzer into the water, and it completes the circuit, and you can measure leakage of probes using water in the Phantom without having to get a separate container, if you will. So lots of reasons I like the Phantom. Again, we don't all have the same ones, I know. If you're doing 3D, 4D testing, you should get a 3D, 4D Phantom. They have those out there to evaluate that. Any other questions? So penetration testing, axial resolutions on all probes, and that's mandated by any accrediting agency. So if you're not accredited, you can say, well, I don't need to do that, which is true, you don't. But it's in your best interest if you do. All of my engineers, we test to ACR standards, whether you're paying for it or not, because I want that information for when I have to go back and troubleshoot.
The form that you use, is that available to us?
Yes, I don't have forms for everyone. I gave everyone my card. If you didn't get a card because you came in later, let me know. Just come up. I have a stack of them right here. Email me. You can get a copy of the presentation. I didn't know how many, so I'm not going to carry a whole bunch of copies. But if you want a copy of this presentation, I'll give it to you, as well as the next one, which again, I don't take credit for. My name's nowhere on it. I'm just showing you, to me, it's a good document to have as a reference. Whoever did it did a really good job, as well as an ACR. Mine's just a Excel spreadsheet. It's several pages long. Tabs are at the bottom. Tells you this is what an OEM requirement for a PM is. The next tab is for NFPA. If you're doing an NFPA 99 electrical safety test, all the requirements for the safety test. And in the next tab is your ACR. So the additional tests that are required for ACR. It's all on one form, so the different tabs. And it goes on with more tabs because we made room for up to 12 probes, but the first 4 on the first tab and then 2, so on. So. Any other questions? All right, let me change to the other presentation real quick. I'm not sure you guys can read that. I know it's kind of hard. Again, this is I can get you a lecture. In fact, if you want, I have it on the thumb drive. If you guys have a device, you want to come up and download it real quick, I have it on the thumb drive. But this is a really cool document. Like I said, it's 8 pages long. And it talks exactly what you're trying to do with all the tests that you can possibly perform on a Phantom. Starts off with dead zone or ramp down. And it talks about exactly what you're trying to accomplish during this test. And then it goes on and says the testing procedure. So it tells you the background of the test, basically. Here's why you're doing this test, and here's what we're looking for. And then specifically, how to go ahead and complete the test. So this is page 1 of it. Ring down testing. It talks about the dead zone is a distance from the front face of the transducer to the first identifiable echo. Okay, and you can't see very good here. You can in the actual document, believe it or not. There's some objects right here, and you saw them on the Phantom. They're at the very top of the Phantom, and they very gradually go to a different depth. And they use this test because the higher the frequency of the probe, what's the advantage of a higher frequency probe? It's better resolution, but at a very shallow depth. So that's exactly what the ring down is saying. At what depth will it be able to detect the first object? Because the lower the frequency, the deeper it'll have to go before it has the time delay to be able to detect an object at all. So on the Phantom, they give you the ability to talk about that. And that's these objects right here. You can see they start at the very top of the Phantom and then move their way down. So that's a test they're trying to describe here, and tells you specifically how to use it or how to do it. Higher frequency, you should expect a shallower depth, meaning it will be very shallow when you'll be able to see an object, where a lower frequency will be a little deeper. Right, so that's one test. Again, I can blow this up so you can read it, but then I can't page, which is, kind of gives us an idea. It's a distance from the face of the transducer to the first object you can see. The dead zone occurs because it can't send and receive. That's the time delay I was talking about, right? It has to have time to go out, hit an object, and then come back and be able to detect it. No clinical data can be collected in the dead zone, which I just mentioned at the beginning of the presentation. We're now up to 33 megahertz, I think, is a highest frequency probe I've ever heard of. And now we're getting in where our dead zone's almost non-existent, which is really cool. But you can't look at something that's more than just surface oriented. So, and it tells you scan the Phantom dead zone target group is clearly displayed, freeze the image. So you freeze it, and then you measure and try to define how deep it is that you can see. Pretty easy test, nothing really exciting about it. Should you do this? I don't do it on every probe, but I will do it on a higher frequency probe. And you say, well, why? Well, because if you have a low frequency probe, do you care about your dead zone? No, because you're looking deep. That's why you're using a lower frequency probe. So it's my rule of thumb, when I'm using a high frequency probe, I'll do this test. 15 megahertz, I'll do the test. But if I'm using a 5 megahertz probe, I'd never do the test because I'm never going to be looking there. If I was looking up there, I'd be using a higher frequency probe to get a better image, right? So just a little background on why or when to do that. And then we can scroll down, we see the picture, and in the results, which I couldn't fit on there without making it too small, but the system's dead zone should remain consistent from week to week when using the same instrument settings and Phantom. So here again, degradation over time is what we're talking about, right? If you don't have this, you have a high frequency probe and you never tested this, then you won't know from week to week or month to month whether it's changing. So again, compare the test results obtained from the baseline records. If the current image demonstrates changes in the system's ability to resolve these targets, corrective action should be taken, okay? So it tells you what the test is trying to accomplish, tells you how to accomplish a test, and then tells you the results that you should be looking for. So, and it's in very clear English. That's one of the reasons I love this document. And then it moves on for the second test, which is geometric accuracy. And they talk about vertical in this case, and tells you about the reason you want to do the test. Okay, and we already talked about that. When you're talking geometric accuracy, what are we talking about really? Anybody remember? Calipers, yeah, we're going to check to make sure that our calipers are measuring accurately. And why would we care? All our calculations are based on that, right? So we want to make sure that what we think we're measuring is accurate. In this case, it's vertical. It talks about temperature, and I kind of mentioned this on my Phantom. I kind of mentioned it. if you're traveling around, if you're in your hospital, it's almost always at room temperature, right? But if you're traveling and this is in your trunk, it will affect your caliper measurements if you have a frozen phantom versus a super hot phantom, right? I mentioned 120 and then going up to Flagstaff and have it freezing. Well, that's going to affect it. These in the old days, I assume they still do, but have temperature strips on them. So if you don't know if it's running hot or cold, it'll help you. But if you know your phantom's been in a 128-degree trunk and you're bringing it in for a PM, you can put it in a sink of water, room temperature water, and that phantom will come to room temperature or close to room temperature very quickly. So, and yes, you can fully submerge this one and it won't hurt it. So temperature does matter is a point. And then you go down, tells you how to accomplish the test, which is super easy, and the results that you should expect. So it doesn't say in here, for example, for vertical or horizontal, what the requirements are for accrediting factions. ACR has a 2 centimeter rule, or 2%, whatever's greater. So they give you some variance if you don't get it exact. And 1.5. So 1.5 for axial and 2% for lateral. So you have variance that you can accept that it would still keep it in tolerance. It doesn't mention that on this document, but you can see you're talking about the same series of dots that I described, and this isn't my document. I didn't create this, but you can see they're using the same style phantom that we use, which is the 539. Any questions on that? Vertical measurements. Our form calls out for 2 centimeters vertical and 2 centimeters horizontal. What's the advantage of doing larger measurements?
Larger variance.
You'll get less variance.
Well, yeah, right.
So now your 2% becomes a bigger number, right? So there is some reasons that you may want to take a larger measurement than 2 and 2. We use 2 and 2, but I just like to point it out. It won't vary over distance. It'll just be how much you're moving, because just a tiny bump of the trackball and you can be 0.03 difference. And so it's how you're measuring it. Now we're talking geometric accuracy, horizontal, same test, different axes. Tells you how to do it again, very simple ones. And now you can see that you have the 2 that you want to measure. This image, can anybody tell me something wrong with this image? I just noticed this for first time. It's unusual. I just noticed it. The image is backwards. And so somebody didn't orientate their probe correctly, because you have a marker. This is called the marker. It's not normally greens. GE may have a GE up there. Philips may have a P up there. AccuSun has a little A up there. So they do it differently, but it'll be on one side of the image or the other. And there's a marker on the probe scan head, and you have to make them look the same, or you'll get 180 degrees out. And you can see your resolution array goes this way while this one goes this way. So your measurement that they're describing here is these right here, but it's backwards. And again, as I said, I would never do these 2. I'd leave it at these 2 because they're 2 centimeters defined. All right, so testing procedures described, and then the results are at the bottom. Okay, again, week to week. Again, we want to see consistency over time, right? No degradation over time. And then we go on, we talk about axial resolution, the ability to differentiate different two objects that are very close together, and know they're two objects. Tells you why we do it, tells you how to do it, and tells you the results you expect. Again, it's very clear English. I like this form because of it. I hand all this to my junior engineers. We go over it in class so that they understand it thoroughly, but then they always have a point of reference. They can always say, I don't remember what I'm trying to accomplish here, and this is good for them. So focal zone. Everybody kind of remembers I was talking about focal zones earlier. I don't have a really good picture of them. They're normally over here where they're an arrow or a bar that you can change the length of, right? And what it's describing again is in this picture, these lines that go from top to bottom that are curved aren't real. They're describing where the technologist is specifically focusing. So that's where your resolution is going to be the best for this image. So it tells you how to do the procedure, tells you the results again. Again, I'm not trying to go over each one of these steps again and again. Then we have the system sensitivity, which is at the top, which is what's a real definition of system sensitivity? Penetration testing, right? So that's what we're really talking about. They'll see it on an ACR form as system sensitivity / penetration testing. But again, it defines the objects they want you to use, which are these objects here that are very dark and very hard to see. When you have the right columns, there are actually, it goes just like this. There will be 3 at the top and then 5, 3, 5. Every other one has 3. And you can see that on the Phantom. We pass it around. We're looking at the ones that are the smallest. So we want to measure these objects right here. And it becomes less subjective. If you can't see the object, if you're saying, I think that's it, it's probably not worth recording, right? We're not here to try to wonder if that's the object or not. If you can't definitively tell me it's the object, then don't record it as that. Otherwise, the next guy comes in, he records it as something completely different, and now you look like you have degradation over time, right? Resolution image uniformity tells you again why to do the test, description of the reason. Oops, where'd it go? Why it popped down 2 pages, but it did. So there's your description and reason for the test. Then it goes on and tells you how to conduct the test. And again, I don't know why it's being painful, but there it is. Then you have your grayscale test. Tells you again how to perform it, which is contrast resolution. And for whatever reason, when you actually look at this Phantom, this object here gets very, very difficult to see on many systems. So that's the one, for whatever reason, I can't explain why that one, but many systems you'll have a hard time seeing this particular object. It's the one that's -3. Okay, it will disappear. And what's that tell you about the system? What are we basically saying if you can't see that object? Clearly it's there. Not the probe. It means that the system is having a hard time resolving between 0 and -3. It can't tell the difference. And it's not a probe related issue, it's a system related issue. That's why I wanted to bring it up again. We only test one probe on this test because the probe shouldn't affect it. only the system's ability to resolve it. Okay. So if this one's gone, does that mean you have a problem? Not if it came out of the box brand new. If they roll it into your hospital and the very first day you're testing it before you put it into service, it's not there, you know it's a limitation of the system. But if you don't do this test and a year later you do your first PM and you can't see it, has there been degradation over time? Well, I don't know. So keep that in mind. That's why I highly recommend taking these images, having hard copies. That's it. That's the 8 pages. Again,